Hi and welcome to part 2 of the motion capture tutorial. In this video, we continue to solve a quite tricky task: reconstructing motion capture with a moving camera filmed with an anamorphic lens. What happened in part 1? It was demonstrated how to set up a motion capture project containing a main camera and 2 witness cameras, including syncing all sequences and cameras. Further, background markers and markers on an actor's face were tracked. Doing this, some tips and tricks considering 2D tracking and organizing points were shown. Part 2 here is all about adjusting camera parameters for succeeding in reconstructing the shot. This will be a hell of a calculation trip with many ups and downs leading to ups again. So let's fasten our seatbelts. There's a lot to do. At first, restore the status of the end of part 1. Everything's tracked, synced and organized. For doing that, we will import a so-called 3DEqualizer merge file. It contains all objects, tracking and lens data. Many thanks to Helder for this awesome script. To have a clean start for importing new objects, let's get rid of all existing within the object browser. Then select 3DE4, File, Import Project as 3DEqualizer merge. In the upcoming requester, click button File Name, and within the tutorial folder, select file mocap all tracked. OK, and a second requester pops up. Here, we can define as which point group type both point groups in the file should be imported. Typically, these settings can be left unchanged. But we have no need to separate the objects in the file from those non-existing in our project, so remove the prefix. Continue. And here we go. 3 cameras, 2 point groups, 3 lenses, and a bunch of points were imported. Good. But why do we see black footage? 2D points are moving throughout the sequence. It seems the files are missing. Let's select the camera for a quick look on the footage settings. As we can see, the path through the footage is leading to nowhere in our machines, since this file was created on a different computer. So we have to correct this by re-importing the sequences. But please be aware that importing a sequence will override all settings considering start and end frames, unless you select the exact frames from the sequence in the folder. But keeping 2 numbers in mind, importing the sequence and entering these 2 numbers again will be much quicker. So let's do that. Keeping 43 and 301 in memory, then import sequence shot 0355. Finally, set start to 43. End was left unchanged. Next camera, same procedure. Here, our 2 numerical friends are 83 and 341. Again, import footage. This time, sequence witness cam left. Last, set the duration to the correct length. Great, 1 camera left. Having 79 and 337 in mind, the right witness camera sequence has to be imported. One last time, modifying the duration. Perfect. As we noticed, there were buffer compression files within the footage folders, so let's import them. Alright, everything's imported and set up. We are ready to face the daunting parameter adjustment marathon. Let's start with the cameras. The very basic step is adjusting all lenses individually to get the best result for each of them. An individual adjustment prevents any of the cameras having any influence on each other. For doing that, the sync constraints have to be removed. We will sync them again later in this video. We just like to adjust all lenses on the basis of the background survey. So to speed things up, as many objects as possible will be disabled. First, adjustment is done with the main camera, so both witness cams have to be disabled. Further, point group mocap as well. Just the main camera and point group camera are left, so let's calc the project to see the current status. Deviation is totally unacceptable. All 2D tracking data is correct, we made sure of that in part 1. So obviously the current lens parameters are far away from being good. So let's get straight to the lens. Having multiple lenses in the project, a quick way to find the lens associated with the current camera is right-clicking on the camera and select script, select lens. Boom! The correct lens is now selected, as well as tap lens showing its attributes. For adjusting lens parameters, we need pane parameter adjustment, so add it to the display area. Great! We start with a quite basic adjustment for anamorphic lenses. Let's add focal length, all degree 2 parameters, lens rotation, and squeeze X. Quite a lot to adjust, so we should set all to adaptive and use the mighty power of network calculation. Everything set, so adjust. As we can see, the deviation value is improving impressively towards a far more acceptable number. Great! Transfer parameters and calc again. Yes, deviation was reduced to approximately 1.1 pixels. That's a tenth of the previous deviation value. Just done with a single basic adjustment procedure. So, the number is great, but how does this result look like? Let's switch to lineup controls. For a better view on the results, let's modify some parameters. Disable the horizon line in menu view. Further, the green crosses could be a bit smaller, so change their projection mode. Finally, all frames showing the virtual clapperboard naturally provide insufficient 2D tracking data. The markers are simply not visible. So let's shorten the playback range a bit. Perfect! Play the sequence. We see all 3D points are placed upon the markers in the footage. Looks quite good. But there's room for more. This ISCO anamorphic lens has some really weird effects towards the edges. This, combined with having a quite low focal length, all degree 4 parameters should be added to the adjustment as well. This will increase the adjustment time pretty much, but also has a high chance to result in an even much better lens reconstruction. So add all of them to the pane. Of course, also with method adaptive. Finally, adjust. As predicted, deviation improves further and further. It was nearly halved. Transfer parameters. Calc all. Boom, now we're getting the pleasing results. Main cam finished. This procedure has to be repeated for both witness cams. Therefore, main cam has to be disabled. And camera witness left will be enabled. At first, calc all to see what's the current deal. Over 4 pixels, as bad as expected. It's pretty sure other parameters will be adjusted with this camera, so clear parameter adjustment. Then select the associated lens. Following parameters are needed for the upcoming adjustment: focal length, distortion degree 2, and distortion degree 4. Unlike the anamorphic lens, this is a pretty standard radial lens, so these 3 parameters will be sufficient. Adaptive all, and adjust. Here we go again. Deviation is improving tremendously. Transfer parameters. Calc all. Great result. An adjustment marathon was promised, So on to round 3. Disable witness left, enable witness right, calc all. As usual, bad deviation. Clear parameter adjustment. Select the lens. Although there aren't many left which should be adjusted, we play safe. Again, add focal length, distortion degree 2 and distortion degree 4. Adaptive all, adjust. Also again, good deviation now. So transfer parameters, calc all, perfect. As intended in the beginning, all 3 lenses were adjusted individually to get these great results. So, time to try everything at once. At first, let's enable both disabled cameras, then point group mocap. Next, synchronization will be turned on again. Set our main camera to primary with no constraints. Both witness cams are the secondary cameras with position and rotation fixed. Okay, so good so far. A last quick look on all 3 deviation values. 0.6, 0.4, 0.2. Really good results. 3, 2, 1, calc all. We notice this procedure takes a bit longer since much more data is used. Okay, what happened? The deviation for main camera increased to nearly 6 pixels. The deviations of all 3 cameras are much higher than before. Let's have a look at results in point group mocap. Based on the deviations here, we cannot be happy either. Let's have a visual check of the results. Since the main camera is, like the name indicates, the main shot which will be used in the final film, we will focus on this camera from now on. With a nose point selected, scrub through the shot. All points are very shaky, definitely not something we can deliver to the other departments. Also have a look with point group camera activated. Yeah, that's really a mess. Switch to 3D orientation controls for checking all reconstructed 3D points in world space. The image plane is a bit disturbing and won't be needed in this video, so let's hide it. Okay, zoom in for a closer look on that green point cloud in front of the survey. Select any point to center it on the screen. What do we see? These are the reconstructed points from the face markers. We indeed can easily recognize the actor's face. When playing the sequence, those points are moving accordingly to the facial movements within the shot. Well, at least most points. There are some big errors and weirdly moving points at mouth and nose positions. Pretty obvious, there's work ahead to fix this. But before we continue optimizing the reconstruction, let's model a face using lines and meshes. This will enhance the visibility of reconstruction errors and the face itself in general a trillion times. Okay, we start to outline significant parts of the face: eyebrows, nose, mouth and chin. Select points belonging to the left eyebrow, then Alt and L to create a line. Great, the same with the right eyebrow. Next, the nose. Very good. These points seem to belong to the mouth, so we create a loop line to reconstruct it. Finally, the chin. Good. Much more recognizable, isn't it? Let's play the sequence. We can see all lines are dynamic and move accordingly to its related 3D point positions. Pretty cool. Last item of this modeling chapter is creating a 3D mesh of the face, which is as easily as creating the lines. At first, select all points except the ears. Then, 3D models, create, mesh from points. Since the 3D points are so close to each other, set filter to 0 to avoid any smoothing. Here we go, we got a mesh. The face is still recognizable quite good. Of course, we should optimize this mesh a bit. For example, let's cut out all polygons belonging to the mouth. Well, it's hard to see which polygons actually belong to it. Having the footage on the mesh would help tremendously. Surprise, surprise, of course, 3DE4 has such a feature. To enable it, either select the mesh directly in display area or from the object browser, more specifically from submenu 3D models of the mocap point group. Having it selected, use the chance to give it a fancy name like, I don't know, face. Pretty fancy, right? Here, in tab 3D model, we find our desired option. Map footage on polygons. Activate it, and magic, the face appears on the face. Great, now we have a good overview of points belonging to the mouth. To remove polygons from a mesh, simply activate Remove Poly and click on these polygons that should be removed. We don't need you, and you. Nice. All editing is done, and we'd just like to view the map footage from now on. So, disable the slightly disturbing lines showing the polygon's edges. Play the sequence. As we can see, the mesh is dynamic as well and moves its polygons according to the movements of 3D points. What do we think about the results so far? It doesn't look completely false. Well, let's not kid around. It's far away from being good. Change to line up for a different view at the mesh. Here it is even more clear how wrong some points move. Especially this point from the forehead shouldn't be there. Clearly, there's insufficient tracking data to reconstruct this point correctly. In this part of the sequence, only 2D tracking data from a single camera is available. This is way too less. So, we have to track this point in at least another camera. But how should we do that? Obviously, the marker isn't visible in the current frames. The solution is a bit inconvenient. We have to guess the marker position and track the point anyway. Sounds silly, but if done approximately right, it will help. Let's start. Switch to manual tracking. And starting with frame 1, we really just guess the position of the marker, which is currently hidden by the face and the other markers. Giving it the thought, the marker has to be approximately here. Okay, since we won't track a marker now, the point's tracking mode should be changed to pattern. Change the tracking area size a bit, then go. This pattern could be tracked quite good. Just a few adjustments were needed for the transition to the truly marker tracked frames. Let's see if it worked. Back to line up. And calc all. Wow, perfect! The 3D reconstruction is way more accurate than before. Of course, this shouldn't become the standard of tracking points. Especially when tracking points for a camera reconstruction, this is a no-go and would cause falsely reconstructed camera paths. However, dealing with mocap points, every point is reconstructed individually. So modifying, or let's give it a name, faking tracking data to improve this single point is possible and can be an option if nothing else can be done. So from the 2D tracking side, everything's fine. From now on, we focus on adjusting parameters to get the solve we can deliver without the risk of being fired. Therefore, in this chapter, we will consider a possible time shift between our cameras, optimize lens parameters, and have a closer look on how all cameras and point groups might affect each other. Alright, we start with syncing problems. During filming, these three cameras were in sync by hardware, but recording was started individually by hand. It's easy to guess there might be a subframe shift between all shots. Let's check this with the help of the virtual clapperboard seen in every camera. Looking through the main camera, all numbers are clearly visible and sharp. They clearly differ from each other. Same with the left witness camera. Looks like there isn't a big shift between these two cameras. Switching to witness right, we instantly see number 5 isn't that sharp like before. Parts of the upcoming 6 can be already seen in this frame. This camera started to record slightly shifted to the other cameras, which can have a big impact having such a fragile construct like a motion capture project. So, how to calculate such a time shift? In the camera's attributes, at the already known synchronization settings, we find an option to adjust time shift. Like every other adjustment, this will take place in parameter adjustment. So, let's add this pane again. All parameters from the previous lens adjustment are still listed. We should clear the entire pane. It would be silly to adjust time shift for all cameras. One always has to be the reference. So we have to choose 2 of the 3. In our case, it makes sense to adjust both witness cameras and use the main cam as reference. Therefore, select just these 2, then enable option Adjust Time Shift. Both parameters are now listed in parameter adjustment. Since we do not know anything of the possible shift range, let's set both to wide. Finally, adjust. As we can see, time shift really has an influence on the reconstruction result. Deviation improves a bit, we are getting a nice valley structure, clearly showing the dependencies of both parameters. Transfer parameters. The adjustment procedure found out the cameras are shifted nearly a half frame and even an entire frame compared to the main cam. That's huge! Calc to see the improved result. But before, let's keep the current deviations in mind. Well, it improved a bit. Let's have a visual check in camera witness left. Having a closer look at the scene, we quickly notice mostly all reconstructed 3D points are far away from their 2D tracking position. Way too far they should be, having a deviation of nearly 2 pixels. What happened here? It's simple. Time shift is applied to the 2D tracking data and isn't displayed automatically. Like it is possible to display 3D points with or without lens distortion correction, time shift has to be activated as well. We can do that by activating View, Show Rolling Shutter Time Shift. All 2D tracking positions were corrected according to the calculated time shift values. Their deviations displayed in Display Area are again matching with the one in Deviation Browser. When scrubbing through the sequence, we see how much or how less their positions vary, depending on the speed the markers in the footage are moving. Okay, seems time shift was another important step forward, but not the solid solution for the mocap problem. After adjusting all 3 lenses and time shift individually, it occurs we have to play hard and adjust everything together. So, back to our favorite tool in this session. Parameter adjustment comes back to Display Area. Of course, clear all listed parameters. Now, every parameter we adjusted previously in this video, yes, not kidding, all of them, are added to parameter adjustment. All those focal lengths, degree 2s, degree 4s, and of course, time shift. 21 parameters in one adjustment procedure. Oh boy, this sounds complex, but necessary. In this step, more than ever, we need adaptive all. Then 3, 2, 1, adjust. Quite fast, it becomes clear this step definitely made sense. The deviation value quickly decreases, which really shows the influences of all parameters. Our calculation marathon is finished, so let's calc all to see the results. Again, keep the current deviations in mind. Calc all. Yay, deviation improved a lot. Great. A quick look at the deviations of point group camera. We're nearly back to those results of the shots calculated individually, without mocap included. That's really great. But numbers aren't everything. Again, a visual check of the quality. That's a bummer now. Deviation values are so great, but the camera is shaky in every frame. Not good. What about the mocap points? Change to their point group and have a closer look. Not so good either. In general, they are projected quite correctly on the markers, therefore reconstructed quite correctly in 3D space. But also, they are shaking way too much. Everything simply too noisy. Seems like, despite all good deviations, all cameras might disturb or influence each other in a bad way. A first idea to handle such a situation is modifying the influences. One camera should be more important, so get a higher weight during calculation. Since the main cam is naturally the most important camera, we also should tell that 3D's calc core by increasing its calculation weight. Let's say to 100. Now all tracking data of this camera is taken 100 times more into account than those of the witness cams. In theory, this will improve the stability of the main cam, but definitely at the cost of the witness cam's reconstruction quality. But as mentioned, the main shot is the one that will be delivered, so we focus on it. A higher weight is set, so again, calc all. Just wow! Deviation improved from approximately 2.3 pixels to 0.08 pixels. Nice! It's very promising, so let's have another look at the 3D points of both point groups. At first, it's already selected mocap. Scrubbing through the sequence, we see nothing is shaking or placed wrong. Just perfect. Next, camera point group. Deviation improved as well. Good so far. So select a point. And what the heck? Still shaky. How can this happen? This error comes from an option enabled by default, in most cases reasonably enabled by default. As seen in the attribute editor, point group mocap affects the calculation of synced cameras. This means all mocap points from all three sequences are being used to calculate the camera path as well. The natural noise of the mocap points have a huge influence on the camera, hence all the noise is transferred to the camera as well. We should try it again with the effect option deactivated. So, calc all again. Deviation didn't change much. Let's select a point to check the quality throughout the sequence. Marvelous! Glued to their markers. Perfect. Check again our glorious mocap points. What's going on? All points are vastly shaking now. Which developer must be tarred and feathered? Although that would be quite cool, there's an explanation for this behavior. Having a closer look at the points, we notice all points are shaking very similarly. It seems the problem isn't with falsely reconstructed 3D points, which should result in completely differently moving points, like we've seen before in this video. This indicates a problem with the entire point group, more specifically, how it is seen through the camera. So, what happened to the calculation of the camera path? After every calculation, A so-called post filter, whose settings can be found in the point group's attributes, is applied to the camera's translation curves. The camera's motion path is smoothed out by the post filter, resulting in falsified camera positions. With the effect calculation option activated, due to these falsified camera positions, its rotations have to be oriented to the mocap points and their motion, making the camera consistent to them. Without this option enabled, all the noise of mocap points is left out. They have no influence on the camera's rotation. This, of course, leads to an inconsistency between the cameras and mocap's motion. Working on a project requiring such a high precision like a motion capture project, this is highly counterproductive. So, when having a shaky mocap point cloud and not just a few shaky points, we should try to disable the post filter in order to avoid any filtering, leading again to a camera path consistent to the mocap points. So, set parameter post filter mode to off. Let's see how this will affect the results. Drum roll. Yeah, looks very promising. All points are moving precisely as they should. Great. So, fingers crossed, let's check the camera. Hooray! Finally, we managed to solve camera and mocap for the main camera. But what about the witness cams? Naturally, we focused hard on solving the main camera. How did that turn out for the other two? Let's switch to witness left and have a closer look at mocap points. That doesn't look right. Same story with witness right. But should we fix that? The following steps are quite optional, since in most cases only the main shot matters and only the main shot will be delivered to other departments. But sometimes witness shots do play a role, so should be delivered too. In that case, they should have at least an approximate reconstruction quality than the main shot. This last chapter of this tutorial tries to improve the witness cams without losing any of the main cam's quality. Okay, let's get started. As we remember, we disabled any affection of mocap points for synced cameras. We should enable this again to include these points again to the calculation procedure. Enable the option, then calc all. Deviation improved from 4.9 to 2.9 pixels. It got better 40%. Good. Let's have a look at the motion. It got better, but is still shaky. A comment on this topic. It cannot be emphasized enough how important it is to sync cameras by hardware. Here, we have a perfect example of the huge problems and troubles unsynced cameras cause. The time shift adjustment is helpful and reduces the effects of not properly synced cameras, but it doesn't solve the problem. This rookie mistake is unbelievably done even at high-end productions. Be cleverer and avoid it with hardware syncing. It will save you time and troubles, as well as the departments working with your shots. Back to the project. Witness cams improved a bit, but what about the main cam? Cool, its quality is as good as before. So far, everything as wished. To improve the witness cams further, an advisable way is to readjust all parameters after we modified so many of those parameters, defining the relation between camera and mocap points. Their settings are of course also taken into account when optimizing lens parameters. So please feel free to play around with another adjustment marathon. In this video, just to save some time, we will skip this step. Another option for improving is editing another filter 3DE4 applies after calculation. All mocap points can be filtered individually. More precisely, their movements along axis Z can be filtered individually. Playing around with the filter strength or even disabling it will affect the point's movements, therefore the visual quality. Again, feel free to play around with this option. Okay, we're finally done. The last tool shown in this tutorial is option Overall Motion Extraction, which extracts the movements of all mocap points composited to a single null object. It puts the movement of the point cloud into the null object of point group mocap, giving us a parented object which might come handy when exporting the project to compositing or 3D animation software. For doing this, simply select Extract Overall Motion automatically. Calc again. And here we go. Motion was extracted. And we even got the point group's motion path, which can also be very helpful for further editing. Well, we got to the end. Let's have a final look at our project. For a better view at the reconstructed face, let's modify the view. Activate View, Center View, Parent to Current Object Point Group, and see what this will do. We see the view camera is linked or parented to the point group's motion. This is really helpful when checking the point cloud's reconstruction quality in particular. Great, isn't it? Well, that's it. What a bumpy and adventurous trip that was. We started adjusting all cameras individually, following with including time shift, leading to this adjustment marathon, which finally got us the first usable results. Playing around with the main camera's calc weight and learning about parameters defining the relation of camera and mocap points and their opportunities, how they can affect each other, did the rest. Further, we used lines, 3D models, and differing viewing modes to enhance the visual checking of the results tremendously. All there's left to say is, thank you very much for watching. I really hope you enjoyed this tutorial. Goodbye.